In this problem of rotational equilibrium, we have a uniform ladder 10 meters long and having a gravitational force of 250 newtons that rests against a smooth wall. Coefficient of static friction between the ladder and the ground is a half, and the ladder makes a 50-degree angle with the ground. How far up the ladder can a 750 Newton person climb before the ladder begins to slip? First thing we want to do is draw a free body diagram of the ladder. So there's our ladder, there's the wall, and here is the floor. And so we have a 50-degree angle here. And then we have that it is a gravitational force. Now we draw the gravitational force in the center of the object. So there's our gravitational force. We have a person somewhere on the ladder. We don't know where. That's what we're trying to find. I'll draw my person between the middle and the top end of the ladder. And I'll label this as FP. The other forces acting on the ladder is that at the bottom, there's friction preventing the ladder from sliding out. So the friction must be to the right to prevent the ladder sliding to the left. And so we'll label that as Fs, static friction. With a surface, there's also a normal force. I'll label that as Fn. Now there's one other force. Now it says it is a smooth wall. So the reason they give this descriptor is to let us know that there's no friction between the wall and the ladder. However, there is a normal force. Whenever there's a surface, there's a normal force of friction. So although there's no friction because the wall is smooth, there is a normal force perpendicular to the surface, to the wall in this case. I don't want to label it as Fn, because we already have that label. So I'll label it as Fw for the wall. Now when dealing with rotational equilibrium, what we have to do is first we have to decide where is our fulcrum going to be. And I'll draw an asterisk at that point. We want it to be at one of the unknown forces, and we have three of them. The normal force, the static friction, and the force of the wall. If we make the fulcrum at this point, remember, the forces at the fulcrum do not create a torque. So we've now gotten rid of two torques. These forces do not produce any rotation if this is where our hinge is considered. There's only three torques from gravity, from the person, and from the wall. Now when I write down my givens, I'm going to write down my givens as to the force of gravity, which is 250 newtons. The distance the gravitational force is away, and all of our distances are from the fulcrum. So our distance is halfway, and then our angle. Now to get that angle, you draw a straight line from the fulcrum to the force and in the direction of force. And you'll see that this makes a triangle here. If this is 50 degrees, we want our angle to be up here, and that is 40 degrees. So our angle is 40 degrees for the ladder. Then we have the force of the person is 750 newtons. We're trying to find the distance of the person. We don't know that. And the angle of the person is also 40 degrees for the same reasons. Now the other torque is caused by the force of the wall. We don't know that yet. The distance the force of the wall is away, which is the full length of the ladder, which is 10 meters. And the angle for the wall, again, if we draw from the fulcrum to the force in the direction of force, this is going to be 50 degrees as well. So this angle is also 50 degrees. Now, the first thing we're going to do is get all of those forces, and we're going to do so with translational equilibrium. Total force in the y is 0, and the total force in the x is 0. In the y direction, there's the normal force up, the gravitational force down, and the force of the person, which is down. So we get the normal force to be 1,000 newtons. Then we can get the static friction, because the static friction is the coefficient times the normal force, which is a half times 1,000. We know the normal force from up above. So the static friction is 500 newtons. In the x direction, we have that the static friction is to the right and the force of the wall is to the left. And so we can get that the force of the wall balances out the static friction, and is also 500 newtons. So now if we go back here, we know the force of the wall is 500 newtons. Then we can proceed. We know everything we need except for this one variable. So these three forces produce torques, and we're going to get this distance necessary for all the torques to balance out. So our total torque is 0, and our torque is Fd sine of theta. There's 3 torques because there are 3 forces not at the fulcrum. There's the torque from gravitation, the torque from the person, and the torque from the wall. Determining positive and negative, we see that the gravitational force will make this ladder rotate clockwise as well as the person. The wall will make it rotate counterclockwise, and so the gravitation and the person are negative, and the wall is positive. Now we replace each one with Fd sine of theta, and this is where writing our information like this makes it very easy for this next step. Fd sine of theta, Fd sine of theta, Fd sine of theta. So we have negative 250 times our distance, 5 meters, times the sine of 40, minus, plus and negative is minus, 750 times our unknown, times the sine of 40 degrees, plus 500 times 10 times the sine of 50 degrees equals 0. And now we can solve for that one unknown. And we get the distance the person can be up is 6.28 meters.